muscle mass and function decline during aging. And that's what we'll see here. On the y-axis, we've got muscle mass and strength, and on the x, we've got age. And then we can see that muscle mass and strength peak around 30 years old. And then there's a range for its decline. If it's on the faster slope, that's on the road to sarcopenia. And on the slower slope, that's what's considered normal aging. Now, note that this isn't just a muscle mass and strength story. Muscle mass and strength are also associated with survival and quality of life. So people who have relatively higher levels of muscle mass and strength live longer and have a higher quality of life. But when considering that the decline happens no matter what, can we do better? And if so, how can we do better? I'm interested in flattening these curves so that loss of muscle mass and strength or function, there's no decline. So how can we do that, or can we do that? Well, aging is a biochemical process that happens over many decades. So with that in mind, what's the underlying biochemistry of high versus low fitness at older ages? And to begin to address that question, let's take a look at data from this recently published study, Serum Proteomic and Metabolomic Signatures of High versus Low Physical Function in Octogenarians. And if you're interested in checking out the paper yourself, it'll be in the video's description. So who was in this study? Well, it included 80-year-olds, as shown there by the average ages in each of these three groups. It included approximately equal amounts of men and women in each group. And then there were three groups: high functioning, normal functioning, and low functioning. And note that although these sample sizes for these three groups are relatively small, in a small study like this, when considering there could be large interpersonal variability, you'd expect to see nothing significant between the groups. But as we'll see, that wasn't the case at all. So what did they measure in terms of defining function between these three groups? Well, there were three measures: walking speed, grip strength, and VO2 peak, which is a similar metric to VO2 max. So first, note that grip strength was not significantly different between these three groups. But where there were significant differences in function was VO2 peak, as the high functioning group included masters athletes that had competed in competition. So with that in mind, the high functioning group had an average VO2 peak of 32 milliliters of oxygen consumed per minute per kilogram body weight. That is in comparison to the normal functioning group, who had 20, and in comparison with the low functioning group, which had the lowest VO2 peak of 16.5. So the high functioning group had approximately 2 times higher VO2 peak when compared with the low functioning group. And when considering that VO2 peak as a measure of aerobic capacity is in the same ballpark as walking speed, I'd expect walking speed to also be better in the higher functioning group. And that's exactly what we see: 1.6, 1.25, and 0.83 meters per second, respectively, going from the highest to the lowest functioning group. All right, so now we have three groups that differ in terms of their physical function in 80-year-olds. So now we can go back to our original question of what's the underlying biochemistry that may be different when comparing high versus low fitness in 80-year-olds. So that's what we'll see here. And these are metabolites associated with physical function in 80-year-olds. And I get that the plot looks like it's a giant mess of dots and stuff, but let's break it down. So on the y-axis, we've got negative log 10 p-value. So essentially, those are relative levels, and this is in a log scale. And then on the x, we've got HF-beta, which is a metric of function. If the data is to the right of 0, if metabolites, the circles, are to the right of 0, I put that green arrow there, that indicates that relatively higher levels of the metabolite is associated with higher physical function. Conversely, if the metabolite is to the left of 0, then higher levels of the metabolite are significantly associated with worse physical function. So let's go through a few examples that we see on the plot as we were looking for elucidating the biochemistry that may underlie high versus low fitness. So first, if you're familiar with the channel, two of these metabolites may look familiar. So PC is phosphatidylcholine. C36.5 is the phosphatidylcholine that has 36 carbons and 5 double bonds. And then there's another phosphatidylcholine, PC38.6. That phosphatidylcholine has 38 carbons and 6 double bonds. And if you're familiar with the channel, then you saw in a recent video that these two phosphatidylcholines are biomarkers of the omega-3 index. When there's a relatively higher omega-3 index, and similarly, when levels of these two phosphatidylcholines are higher, that's potentially indicative of a lower cardiovascular disease risk. So now we see that these two phosphatidylcholines aren't just significantly associated with the omega index, but also with physical function, with higher levels being associated with better physical function. Also, if you're familiar with the channel, the next metabolite shouldn't be a surprise. Lyso-PC C18-2. This is a lysophosphatidylcholine that has 18 carbons and two double bonds. And there's also a recent video on the channel where I showed that lysophosphatidylcholines are biomarkers of mitochondrial function. So this would suggest that obviously having better mitochondrial function would be associated with better physical function, but now we have a plasma biomarker of that process, lysophosphatidylcholine 18-2. And as we'll see in a minute, there are many other lysophosphatidylcholines that may be a part of the story. If you missed either of those two videos for the phosphatidylcholines being associated with the omega-3 index or lysophosphatidylcholines, I'll link to it in the right corner. Now, another metabolite that was associated with better physical function is the amino acid tryptophan, and that's what we'll see here, with plasma levels of tryptophan on the y-axis plotted against levels in each of the three groups. And then we can see that when comparing lowest with highest physical function, the higher function group had significantly higher plasma levels of tryptophan. All right, so these are some of the metabolites that are associated with better function. What about some metabolites that are associated with worse function? One of those is the gut bacteria-derived metabolite indoxyl sulfate, or INDSO4, as shown in red with the red arrow. So let's take a look at those data. On the y-axis, we've got the plasma levels of indoxyl sulfate, and then again, that's plotted in those three groups. And here, we can see that now the lowest function group had the highest levels of indoxyl sulfate, whereas the higher function group had significantly lower levels. So these data would suggest that having relatively higher levels of this gut bacteria-derived metabolite, indoxyl sulfate, may be bad for having relatively higher levels of physical function. And again, these are just correlations. I'm not suggesting causation, but this is what the data shows. All right, so note that this isn't just a health and longevity news-focused channel. I'm also interested in practicing what I preach and trying to implement what I find in the published studies to try to optimize my biochemistry towards the most youthful profile that I can possibly have at any chronological age. So with that in mind, what's my data? So to figure that out, I've been using at-home metabolomics with Iolo's kit as shown here, which includes data for tryptophan and indoxyl sulfate, but also 600 plus other metabolites. So if you're interested in using this kit, there's a discount link in the video's description. All right, so let's first take a look at plasma levels of tryptophan over the 19 tests that I've tracked from 2023 through 2025. And that's what we'll see here. On the y-axis, we've got plasma levels of tryptophan, and that's plotted against time on the x. So over 5 tests in 2023, average plasma tryptophan was 28 micromolar. Then over 9 tests in 2024, an average of 32 micromolar. And after the first 5 tests, I'm waiting on results for test number 6. I plan on testing 2 more times this year, so it'll be 8 tests this year. After the first 5 tests in 2025, average plasma tryptophan is 27 micromolar. So are these data significantly different? So to find out, I use a 2-sample t-test, year versus year. And when using that approach, the data in 2023 versus 2024, so 32 micromolar average versus 28 micromolar average, they are not significantly different. As you can see, the p-value is 0.19. All right, what about 2024 versus 2025? There too, that 32 to 27 micromolar difference, not significantly different. P-value equals 0.17. And for those who are unfamiliar, p-value is less than 0.05 is a general threshold for statistical significance. All right, well, what about where I started in 2023 versus 2025, the more longitudinal change? Here too, not significantly different with that p-value of 0.41. From these data, we can see that I've mostly kept plasma tryptophan levels stable, at least based on the stats. Now, an argument could be made that maybe 32 micromolar in my case is better, and that's something I'll look into in future tests and future experiments, but at least based on the stats, no change for plasma tryptophan over this 2+ year level. Which then raises the question, what's optimal for plasma tryptophan? So based on the study in 80-year-olds, relatively higher may be better for physical function. So keeping it relatively high is one part of this equation. But also, and I've covered this in other videos for tryptophan, it declines during aging, so resisting its age-related decline. So with that in mind, this is good news, as I've resisted, based on at least these 19 tests over this 2+ year period, I've resisted an age-related decline for tryptophan. All right, what about plasma levels of that gut bacteria-derived indoxyl sulfate? And that's what we'll see here. On the y-axis, we've got levels of indoxyl sulfate, and again, plotted against time on the x. So after those 5 tests in 2023, average indoxyl sulfate was 1.6 micromolar, an average of 2.2 micromolar over those 9 tests in 2024, and currently 2.4 micromolar over 5 tests in 2025. When running the stats, when comparing 2023 versus 2025, unfortunately, the data has gone in the wrong direction. Indoxyl sulfate has significantly increased over the past 2+ years in my data, is what this trend line indicates. So in terms of what's optimal for plasma levels of indoxyl sulfate, keeping it relatively low may be important for maintaining high levels of fitness at older ages. But also, indoxyl sulfate, and I've covered this in other videos on the channel too. If you want to see those videos, just leave a comment and I'll direct you to the exact video. Indoxyl sulfate increases during aging, so we want to resist that age-related increase. So for this, unfortunately, I'm not following the correlation. It's actually gone in the wrong direction. But these are just 2 metabolites. Is it fair to assume that if 2 metabolites can impact all of physical function or all of aging? I don't think so. And in support of that, the plasma metabolome includes 18,000 metabolites. So although 2 of those metabolites could be something like glucose or maybe cholesterol, which are found in relatively high concentrations, would 2 metabolites at micromolar values be enough to really move the needle in terms of physical function at older ages? So ideally, we'd resist age-related changes for all metabolites. So there's going to be a biochemistry of youth. Now, just using the plasma metabolome as an example, 18,000 metabolites, all of those metabolites are going to have a certain concentration in our youngest, most youthful state. So how much does that deviate during aging? And can we stay closest to our most youthful biochemical profile at advanced older ages? With that in mind, there weren't just a couple of metabolites associated with physical function in this study. There were 56 that were associated with physical function. Now note that Iolo's metabolomic kit includes 55 of these 56 metabolites, and I'll include data in a minute for 54 of these metabolites with the exception of homocysteine, which I find more value in measuring by venipuncture instead of with the Tasso device. So first, let's start off by looking at the metabolites that were associated with higher physical function. And there were 44 of those metabolites. I wanted to get them all onto to one page. So if you're on mobile, I apologize. You're not going to be able to see these data. But if you're on a desktop, I'd recommend going full screen to try to see all of the metabolites that are on this list. So note that there are a few metabolite groups that stand out as potential patterns that may underlie higher levels of physical function, including lysophosphatidylcholines. So earlier I mentioned the lysophosphatidylcholine C18-2, but now we can see that there are many others that are positively correlated with physical function. Now this shouldn't be a surprise because, as I mentioned earlier, lysophosphatidylcholines are biomarkers of mitochondrial function. So higher mitochondrial function, higher physical function, but also note the PC group, the phosphatidylcholines. It's not just those 2 that are associated with the omega-3 index. We can see many other phosphatidylcholines are positively associated with physical function in 80-year-olds. Now note that I didn't say all phosphatidylcholines. As we'll see in a minute, there are a couple that are associated with function going in the wrong direction. And then there's a third metabolite group that may be new to most people on the channel, and that's SM, which are sphingomyelins. So I won't go into what are sphingomyelins in this video, but I'm planning on a future video as they may be linked with neurodegenerative disease. So expect that video coming sooner rather than later. And then atop the list are a couple of metabolites on their own without being associated with any groups, ceramide and glycine. All right, so then note that all of the betas, the beta coefficient, are positive. So again, these are metabolites that are positively associated with physical function in that earlier study. And then the p-value, this is an adjusted p-value to account for multiple comparisons. All of them have the adjusted p-value less than 0.05. So then the big question is, have I resisted age-related changes for these metabolites? And if these metabolites are associated with physical function, not just in 80-year-olds, but at any chronological age, at worst, I want no change year to year for all of these metabolites. At best, maybe even a bit higher, resisting age-related change for their levels. And if these metabolites are involved in mechanisms that sustain and improve physical function, higher levels would be better over time. On the other hand, if they get worse, that's going in the wrong direction. Because if this biochemistry is a part of function, then lower levels of these metabolites may be reflective of lower physical function. And as a quick aside, I'm not trying to say don't do any workouts, don't exercise, just optimize your biochemistry. I'm 100% pro-exercise. It's essential. It's the core of what I do. I'm trying to keep my physical function as highest as physically possible by trying to also optimize my internal biochemistry. All right, so now let's address the question of potentially resisting age-related change for these metabolites. And now what we can see are average concentrations for each of these metabolites from 2023 to 2025. And then you can see that there's green and red on the list. So what does that mean? Well, green is indicative of a higher year-to-year change. So for example, for glycine, I significantly increased it in 2024 relative to 2023. And then the red in 2025 is 2025 data is lower than 2024 data. So if you see green, that means that it's higher than the previous year. And if you see red, that means it's lower than the previous year. And if you go through the list, there's a lot of greens and reds, but what I care most about is long-term change. 2023 versus 2025 data. Because if 2023 data looks the same as 2025, and if this is part of the biochemistry that underlies physical function, then at worst, no change if the data are all stable. And what we can see is that 40 of these 44 metabolites are not significantly different when comparing 2025 with 2023, which suggests a stable biochemistry and potentially no change for physical function if they are indeed related. Now, 3 of those 4 are actually going in the right direction, with higher potentially being better, as higher may be a part of the biochemistry of having higher physical function. So almost all of these metabolite levels are stable, which is potentially good news, as it would suggest that function would be stable. And when considering that 3 of these metabolites are going in the right direction, maybe even slightly higher. But this is only half the story. What about metabolites associated with worse physical function, right? We'll have some metabolites that may positively impact function, but the net effect involves what about metabolites that can negatively impact function? What's the full picture? So that's what we'll see here. And now we've got a few different groups. We've got the amino acid cysteine, but also its oxidation product, cysteine. When cysteine becomes oxidized, 2 cysteines can stick together. That metabolite is known as cysteine. And then we've got the fatty acid with 18 carbons and 2 double bonds. This is linoleic acid. We've got another gut bacterial-derived metabolite, paracresol sulfate. And now we see 2 phosphatidylcholines. So this is why I mentioned earlier that we can't say all phosphatidylcholines are associated with better function. We've got 2 that are actually associated with worse function. And then there are also 2 specific triglycerides. Note that all triglycerides are not a single metabolite. They include many different metabolites that collectively sum into what we know of as triglycerides on a blood test. But there are many different triglyceride metabolites that are comprised in that measure. Also note that these aren't the 2 triglycerides that I covered in a recent video that are downregulated in longevity promoting interventions. All right, so now note that the beta coefficient for all of these metabolites is negative. Higher levels of these metabolites are associated with worse physical function, and these are significant associations as the adjusted p-value, adjusted for multiple comparisons, is less than 0.05. So now going to that question again, have I resisted age-related changes for these metabolites? First, starting with the data for 2023, 2024, and 2025 average concentrations as shown there. And you can see that cysteine increased 2024 versus 2025. That's moving in the wrong direction, especially when considering that higher levels of these metabolites may be worse for physical function, so I coded it red. And then we can see that for one of the phosphatidylcholines, that declined. So lower levels of these metabolites would potentially be good news for physical function when considering that higher levels of these metabolites may be bad for physical function. But again, remember, I care about longitudinal change most. What about the data 2023 versus 2025? So we can see with the NS, that's not significant, 7 of 8 of these metabolites are not significantly different when comparing where I started with where I currently am in 2025. With the exception of paracresol sulfate, which is higher in 2025 when compared with 2023, so that's movement in the wrong direction. So to answer that question of have I resisted age-related changes for these metabolites, now that we've seen 54, including tryptophan and indoxyl sulfate earlier, 54 of the 56 metabolites that were associated with physical function in the earlier study, for 48 of the 54 metabolites, there's no 2-year change, which would suggest, again, if this metabolite group, these 54 to 56 metabolites, is associated or can improve or impact physical function, that the vast majority of them are not different over a 2+ year period, that would suggest that my function may also not be different, or at least the biochemistry related to function may not be different over that 2-year period. On the other hand, 3 of the 51 metabolites have a higher 2-year change, which could be good news when considering that higher levels of these three metabolites in the table on the left may be related to better function. But on the other hand, there are also three metabolites that have moved in the wrong direction, including indoxyl sulfate, paracresyl sulfate, and one of the phosphatidylcholines that are a part of the omega-3 index. So getting those to move in the right direction is atop the to-do list going forward. If you've ever wondered what's optimal for biomarkers, well, I have a new Patreon tier dedicated specifically to that. It currently includes the 35 biomarkers shown here, more than 2 hours of video content, 52 published references, and note that these aren't the reference ranges for what may be optimal, which you can get from any LLM. This is what may be optimal based on how each of these biomarkers changes during aging and or their associations with all-cause mortality risk in the largest studies that exist. So if you're interested in that, check it out. If you're interested in more about my attempts to biohack aging, check us out on Patreon, where I offer blood test consults, and I post at least twice per day in 4 other Patreon tiers. We've also got a whole bunch of discount and affiliate links that you can use to test yourself that help support the channel, including ultralabtest.com, which is where I get the majority of my clinical chemistry blood biomarker testing done, the clearly filtered water filter, which I use every day, at-home metabolomics, which I mentioned in the video, oral microbiome composition, NAD testing with Infinity, epigenetic testing with True Diagnostic, at-home blood testing with SciFox Health, which includes the best epigenetic clock of epigenetic clocks, GrimAge, green tea, drink it every day, diet tracking with Chronometer, or if you'd like to support the channel, you can do that with the website Buy Me a Coffee. We've also got merch, including Data is my North Star, Figuring Stuff Out is my drug, which I've got on here, and the ConquerAging or Diet Trying channel logo. So if you're interested in that, discount link in the video's description. Thanks for watching. I hope that you enjoyed the video. Have a great day.